want to do a brief introduction to coordination compounds. So to do this introduction on coordination compounds, I'm going to specifically be talking about this coordination compound. The way that you would name this is, which we'll talk about later, but this is hexaamine cobalt-3 chloride. We've got 6 amines. This complex ion has a positive 3 charge, and then the counter ions are chloride. So first I want to define what a coordination compound is. And a coordination compound, it's also called a complex, is a substance that contains at least one complex ion. And a complex ion is a species containing a central metal cation, so in this case cobalt-3+, that is bonded to molecules and ions called, and/or anions called ligands. In this case, our complex, this entire thing inside the brackets is our complex ion. The cobalt is our metal ion, and the ammonia, or we call these the amine, are our ligands. And counter ions are also present. Typically, if your complex ion has a charge, then you will have counter ions. And that's just to maintain charge neutrality. And in this example, chloride is our counter ion. And sometimes you could have your counter ion be a whole nother complex ion. And it's important to note that this coordination compound will behave like an electrolyte in water. And when this will dissolve so that you'll have your complex ion and 3 chloride anions in solution. But when it dissolves, this complex ion stays intact. For complex ions, one thing we need to talk about is coordination number. So coordination number is the number of ligand atoms that are bound directly to the central atom. For this species, coordination number is the number of atoms bound directly to our central metal. So here we have 1, 2, 3, 4, 5, 6 nitrogen atoms bound to this cobalt. So this would have a coordination number. Another example I wanted to show you, this is actually something that you're going to be making in the lab this quarter. This ligand is called acetylacetonate, or ACAC. So this is often called cobalt ACAC. So here we also have 1, 2, 3, 4, 5, 6 oxygen atoms bound to our central metal ion. So again, our coordination number here is also 6. It's important to note, I think that this ACAC example is a good example because the coordination number doesn't tell you the number of ligands, it tells you the number of atoms bound to the central metal ion. Because for cobalt ACAC, you only have 3 ligands bound, but you have a coordination number of 6. So if you have a coordination number of 6, this is going to be what we call an octahedral complex, and that's the most common coordination number, but you'll also see coordination number of 2 and 4 as well. So geometry, this is just the shape of the complex ion, and this is just based on VSEPR. So if you have a coordination number of 6, based on valence shell electron pair repulsion theory, you'll have an octahedral complex. If you only have a coordination number of 2, you'll have a linear. If you have a coordination number of 4, the one unique thing about coordination compounds is with a coordination number of 4, when you took general chemistry, you learned that if you had a steric number of 4, that was a tetrahedral complex. But with these complex ions, sometimes you can have a square planar geometry or a tetrahedral geometry. And we'll talk more about how to predict whether it's square planar or tetrahedral in the upcoming weeks. And then octahedral, that's going to be your most common. So that's when you have a coordination number of 6. So this is coordination number of 2, coordination number of 4 for both of these. And this one's coordination number of 6. And again, I apologize for my handwriting. Okay, so we also need to talk about ligands. There are a lot of different types of ligands, but I just want to go over a few examples. The first type of ligand is a monodentate ligand. And monodentate, this mono is the Greek word for one, and dentis is Latin for tooth. So monodentate, this means that it has one binding site, essentially. or only one pair of electrons will bind with that metal atom or ion. For a bidentate ligand, bi means two, dentate again means teeth. So now we have two pairs of electrons bound to our metal ion. So our previous example, ACAC, is a bidentate ligand, whereas an amine ligand is a monodentate ligand. So the denticity of a ligand is defined as the number of pairs of electrons it shares with a metal ion. Another example of a bidentate ligand is ethylene diamine. I'll show you guys what that looks like. So ethylene diamine, most of you have taken organic chemistry, so and again, that's supposed to be a lone pair right there. It's a little rough. This is ethylene diamine. Roughly, you've got an ethyl group, you've got two amines, so it's ethylene diamine. This is another bidentate ligand because you have two lone pairs that can donate to your coordination compound. If you have a multidentate ligand, so more than a bidentate ligand, this is typically called a chelating agent, and this chel word means claw. You can also have what's called a bridging ligand, and this is a ligand where it bridges two metal atoms simultaneously. And finally, you can have an ambidentate ligand. We talked about ambidentate ligands earlier when we were talking about hard, soft, acid, base theory. So this is where you have two atoms on the same ligand that can uniquely donate two different pairs of electrons. So cyano, you can either donate your electrons from, so you have your cyano, so you could either donate electrons from the carbon or the nitrogen. So this is an example of our bidentate ligand. We already talked about this. This is ACAC. So bidentate means that it simultaneously will donate two electrons to your metal ion. So an example of a bridging ligand, it could be something like chloro. So chloro has four lone pairs on it. So one pair can be donated to one ruthenium and another to a different ruthenium. So this is what's called a bridging ligand. This is another example of a bridging ligand. Hydroxide has three lone pairs. It can donate one to one cobalt and one to another. You can also have ambidentate ligands. So here's an example where thiocyanato is donated with the nitrogen on this side, but it also could have been donated with the sulfur. Okay, so that's just a brief introduction to coordination compounds, and we'll continue more with our discussion in class.